Welcome back to Mechanical Design 1 course. We'll continue with topic of stress, strain, and deflection. We'll continue with this topic, deflection in beams. Applied load will cause a beam to deflect. Here we have a concentrated force on a beam, and the beam is sitting on two simple supports. As you could see here, we have wing of an aircraft. This is a Boeing 787, and we could consider the wing of the beam of the plane as a beam. And this is a cantilever beam, so it could be considered as a cantilever beam. Okay, so now we are interested to see how much is the deflection of the beam on each location. So we already managed to find shear forces and bending moments across the beam, but now we want to find the deflection and the slope of the beam. Interferences between moving parts or misalignments is caused by deflection. Okay, so it's very important. That's why deflection is important, to know how much is deflection between moving parts, and specifically parts which they have interferences. And we need to know if that deflection could cause failure of the machine. Minimizing deflections will lead to larger beam cross sections. Deflection can be the limiting criterion in sizing beams. The bending deflection of a beam is calculated by double integration of the beam equation. So here, m divided by ei is equal to second derivative of the y in respect to x. M is bending moment, E is Young's module, and I is second moment of inertia. Y is deflection of the beam, which relates the applied moment, M, the material's modulus of elasticity, E, and the cross sections area moment of inertia, I, to the second derivative of the beam deflection, Y. The independence variable X is the position along the beam lengths. Above equation is only valid for small deflections, which is not a limitation in most cases of beam design for machine or structural applications. Sometimes beams are used as springs, and their deflections may then exceed the limitations of this equation. Above equations also does not include the effects of deflection due to transverse shear loads. The transverse shear component of deflection in long beams is small compared to that due to the bending, and is typically ignored unless the beam's length steps ratio is less than 10. Above equation can be differentiated twice and integrated twice to create the set of 5 equations which define beam behavior. So first, this equation is only valid for small deflection. If we are designing spring and expecting too much deflection, then we cannot use that equation. Plus, that equation does not include the effect of deflection due to the transverse shear load. And we could integrate or differentiate that equation to find some set of equations. Loading function is typically known. Okay, so we need to know what is the loading function, or Q. The constants of integration found from boundary conditions. We'll discuss what are these boundary conditions. If the beam's cross-section change over its lengths, then the integration must be done piecewise to accommodate the change in I. In most cases, the I is constant, so we don't need to get the integral of I, and we could take it out of the integral. The integral forms of the beam equations are, so we already had this equation, Q is equal to dV dx, or Q is equal to derivative of the V in respect to X. So we could get the integral and say V is equal to integral of Q dx plus the constant of the integral. We know Q, we know the loading function, so we should be able to get this integral. Then we again had the equation before that m is equal to the integral of v dx. Okay, so again we see that we'll have a second constant of integral c2 here, and based on the previously explained equation, we could have y and theta. So theta is slope of the beam, and theta by definition is derivative of deflection. Okay, so deflection of the beam is just a function. Okay, so let's say this is or beam deflection. Okay, so we have x and y, and here we have y axis. Okay, so this is just a function, yes, and this one is x. Okay, so this one is x, this one is y, this one is a function, and the slope of this function is a derivative of the y. Okay, so theta is derivative of the y, and second derivative of the y is equal to m divided by ei. Okay, so then we'll end up having these equations that theta is equal to integral of m divided by ei dx plus c1x2 plus c2x plus c3, and y is equal to integral of theta dx plus c1x cubed plus c2 squared plus c3x plus c4. And what is x? X is an independent variable that changes from 0 to L, which L is the length of the beam. Okay, so you see that if we get these integrals and find the constants C1 to C4, then we could have deflection of the beam, which was the purpose of this specific topic, to find deflection and the slope of the beam. The constants C1 and C2 can be found from boundary conditions on the shear and moment functions. For example, the moment will be 0 at a simply supported beam end and either 0 at an unsupported free end of a beam. But there is an easier way to deal with C1 and C2. We'll discuss it in this bullet point. The shear force will be 0 at an unloaded free end. Note that if the reaction forces are included in the loading function Qx, then C1 and C2 will be 0. So if you are writing Qx based on singular functions and are including um, reaction forces on all supports, then you could simply ignore C1 and C2. The constants C3 and C4 can be found from boundary conditions on the slope and deflection functions. For example, the deflection will be 0 at any rigid support, and the beam slope will be 0 at the moment support. So what is rigid support? For example, a simple support, a roller support. We know that deflection on supports are 0. What about the slope? It will be 0 at moment joint. What is moment joint? One example of a moment joint is a fixed joint in cantilever beam. Okay, and it's very intuitive. And you know that in cantilever beam, the slope of the beam will be 0 at the support. Okay, example. What is the problem? Determine and plot the slope and deflection functions for the simply supported beam shown in figure 422A. Okay, so this is an example of the book. You could also refer to the book. And we are looking to find the slope and deflection of the beam. The beam is sitting on two simple supports, and there is one uniformly distributed force that starts from A and ends at L. What are given? The load is uniform over part of the beam lengths. Let beam lengths L to be equal 10 inch. The load location A is equal to 4 inch. The beam's I, or moment of inertia for the cross section of the beam, is equal to 0.163 inch to the power of 4, and E is equal to 30 mega psi. The distributed force is W, equal to 100 pound per inch. Assumptions: the weight of the beam is negligible compared to the applied load, and so can be ignored. Okay, so we ignore the weight of the beam. Okay, so there are two approaches. One approach is to use a graphical method. When we need to find the loading diagram, or Q. Then we need to get the integral of the Q to find the shear diagram. And then we need to get another integral from the shear diagram, and we'll have a moment diagram. Okay, so then we need to get another integral and divide it by EI, okay, to find slope diagram, and again another integral to find deflection diagram. What we need to know is that deflection at supports are 0. Okay, so at 0 and L, deflection is 0. Okay, these are our boundary conditions. Okay, another method is to use singular functions. I already uploaded a couple of problems and examples on Moodle from the book and solutions. So problems and solutions. Please follow those problems and solutions and see how you could use singular functions to solve these type of problems. Okay. This is exactly what you have done to find a shear and moment diagram. What you need to do, you need to just continue integration and find slope and deflection. Statically indeterminate beams. When a beam has redundant supports as shown, it is said to be statically indeterminate. So here you see that we have one extra support. Why am I saying that this support is extra? Because if you remove the support, the beam still will stay in static condition. Okay, so it doesn't get acceleration, it doesn't move. Yes, so it will stay in static condition. So one of these supports are redundant. The magnitudes of more than two reaction forces or moments cannot be found using only the two equations of the static equilibrium, sigma f equal to 0 and sigma m equal to 0. Okay, so in indeterminate beams, we cannot only use these equations. We need also extra equations. To find more than two reactions requires additional equations, and the deflection function can be used for this purpose. So still we need to use sigma f and sigma m equal to 0 functions, but we need to find an extra equation, and that extra equation will be that, for example, here deflection is equal to 0 in the extra support. So what we need to do, we need to find a deflection function and set it equal to 0 at the extra support, and that equation will be our third equation. Okay, so please follow the problems and solutions on Moodle for the topic of deflection and see how you could use graphical and singular functions. We'll move on to the last topic of stress, strain, and deflection, and that topic is torsion. So you see here we have a beam, a cantilever beam, with the circular cross section, and we applied torque. When members are loaded with a moment above the longitudinal axis, they are said to be in torsion, and the applied moment is then called a torque. So we could have two types of torques. One is torsion that will cause some twisting. Okay, so we'll twist the beam, and we could have bending moment, and that will bend or beam. So here we have a torsion on the beam, and you see that it twisted or beam by theta. And here we see the shear stress distribution or tau because of the torsion torque. We could have two types of shear stress. One shear stress could happen because of transverse load or shear forces. The second one could happen because of torsion torques. You see what is the stress distribution for this case? It's 0 at the middle and is maximum at top and bottom. Circular section. First, we'll discuss circular section and then we'll move on to other types of sections. A differential element taken anywhere on the outer surface will be sheared as a result of torque loading. The stress tau is pure shearing and varies from 0 at the center to a maximum at the outer radius. So tau shear stress is equal to T rho divided by J. So T is constant at the particular cross section. Rho is basically the distance from the center. So here at the center, rho is 0 and it's equal to R at the outer fiber here. So the maximum of the rho is equal to R. And J is also constant, is polar area moment of inertia. So T is applied torque, rho is radius to any point, J is the polar area moment of inertia of the cross section. The stress is maximum at the outer surface at radius R. So you see, what is the function here? It's a linear function. T and J are constant and R is rho is variable here. So it's a linear function. So the shear stress due to torsion has a linear distribution. Okay, and see that could be basically either positive or negative. Okay, it's positive here and negative here. What is the direction of, for example, or torque? This is the, for example, direction of our torque, yes, and here it's direction of or shear stresses. The angular deflection due to the applied torque is equal to theta equal TL divided by GJ. T is again the applied torque, J is polar moment of inertia is constant, G is modulus of rigidity is also constant, is a mechanical property, and L is the length of the beam. So where L is the length of the bar and G is the shear module or module of rigidity. The polar moment of inertia of a solid circular cross section of diameter d is J is equal to pi d4 divided by 33. And this one is for hollow cross section. And we need to just subtract the polar moment of inertia for the hollow section. The circular cross section is the optimum shape for any bar subjected to torsional loading and should be used in all torsion situations if possible. Okay, so why we are saying is optimum? Because this circular cross sections will experience the least amount of basically twist. So theta will be the minimum value, the minimum possible value if we use circular cross sections. Non-circular sections. A general expression for the maximum shear stress due to torsion in non-circular cross sections is tau max is equal to T divided by Q. What is Q? Where Q is a function of cross-section geometry. The angular deflection is theta is equal to TL divided by kg. Okay, so we'll see what is Q, how we could find Q based on appendices and tables of the book. T is the torque, the torsion torque applied. L is the length of the beam. G is again the shear module, and K is a function of cross section. So K is a function of cross sectional geometry. So we need to know how we could find Q and K. So we have these tables in the book, and you see for different cross sections, for example, for solid square, we could find Q and K as a function of A. For hollow square, Q and K are a function of A and T, okay, which is basically width and thickness. For a solid rectangle, for hollow rectangle, for solid ellipse and other shapes, you could find K and Q constants. So these are constants. Again, for hollow ellipse, for open circular tube, and for open arbitrary shape. So for these ones, again, Q and K are constants. For open arbitrary lengths, it's based on U and T. So T is thickness, and U is length of median lengths. This is again example of the book to see how we could find deflection theta for different cross sections of a constant torsion torque T. So in this example, we want to find and determine the best cross-sectional shape for a hollow torsion bar to be made from a sheet of steel of known dimensions in order to withstand a pure torsional load with minimum angular deflection. Find the max shear stress. So we want to see between these options: A, flat plate; B, open circular; C, closed square; and D, closed circular, which one will have minimum angular deflection or will have the minimum theta. And also we need to find the maximum shear stress or tau. So T is equal to 10 Newton meter, L is 1 meter. This is the length of the bar. Okay, so this is a cross section, for example, here for the closed square. What is the length of the bar? The length of the bar is 1 meter for all of these. T, or the thickness, is 1 millimeter, and G is constant for all of these because they are made of the same material. Okay, so intuitively, we could guess that A and B will experience highest value of angular deflection, and C and D should experience the less because they are closed sections. And as we said, circular cross sections have optimum value in, angular deflection. So um, even without solving, we could say that D has the minimum angular deflection and is the optimal one. But I expect you to follow the solution of the book and see basically how much will be the theta and maximum tau for each of these cross sections.